ductile iron and IDI. That I will explain now more what it is. And this presentation will concentrate on two subjects. How do you? Okay, this one? No, next. Okay. This presentation will concentrate on two subjects. The first subject is the comparison between two ferritic ductile ions, and the second part will focus on the plastic assessment, the plastic behavior of this material, while Stefano was considering the crack propagation. The second subject, the plastic deformation, is necessary to be considered for two main issues. The first one is the process control that we get with the tensile test, and the second is giving to designers the confidence on our material, mainly ductile ions, comparing with steel, and showing how we are able to use the plastic flow curve in considering the designing when overloading and impacts are concerned. That is one main limitation for the more wide development of ductile iron in comparing with steels. So, what is isothermed ductile iron, namely IDI? It is not a different kind of ADI. It is simply a ferritic ductile iron. And that is competing in the range of 500 megapascal yield strength with high silicon ductile iron and with high-performing ferritic ductile ions as Fiat grades or cyberdual coefficient. And this material, isothermed ductile iron, that is a neologism, is obtained with no alloy. Before we were talking about segregation of copper, segregation of moly, of elements that we add to the material. Here we make no addition. Simply we cast a common conventional ferritic ductile iron with a silicon content as is good for our casting. Could be 1.8, 2%, 2.5, 3%, and 3.5. Doesn't matter. Then, what we are doing is the austenitization in the intercritical range AC1, AC3, and we catch into the soil, a soil bath. So, above the martensite start temperature. This means that we are not getting a ferritic reaction as in ADIs, because having no alloy, the buying curves are stable on the left. We are not pushing on the right. And so we cross the ferritic nose. However, when we are crossing the ferritic nose driven by the soil bath quenching, the eutectoid transformation happens in minutes. And so the difference between a 25 thickness to a 75 thickness is simply from 1 minute to 3 minutes, and not as it happens in the mold from 1 hour to 2 or 3 hours. So, first of all, we have no segregation, except silicon, in a eutectic when we have the solidification, and we have not a mobility of carbon during the eutectic transformation, so the ferritic transformation happens in situ. And this means that the structure, microstructure, is not the bullite that we know, but is a structure that at the beginning of this invention was calling leopardite, like a leopard skin. And then that we call it in the patent perferritic. Perferritic is not ferritic, but is evoking a perfect perlitic-ferritic structure, where the ferrite is a continuous, connected, and not separated by perlite, and where perlite is reinforces the ferrite structure, giving more strength, giving more yield, and conserving a ferrite content able to maintain ductility. So, in this way, we obtain the same properties of a fully perlitic ductile iron, but with a significant fraction of ferrite. So here you see an example, this magnet simulation of a casting that we produce in ADI, is a suspension for a heavy truck, 72 kilograms, that we made a qualification in IDI with successfully and with the same functional results. So here you see the comparison of the material that Stefano was presenting before in respect of fatigue with the fracture mechanical concept for only the two materials, that is perlitic, ferritic, conventional ductile iron, the red one, that is cast in the mold, and the isothermed IDI, the perforatic ductile iron, the black bars, that is obtained by a treatment. And so you see that, and the Brina harness that you see on the right is similar, so only 5 points different from one grade process to the other process, so similar harness, but you see in the first, in the upper figures that we have for the same harness higher strength, ultimate tensile strength, and uniform tensile strength, 25, 50, and 75 millimeters. Same happens for RPO2, the heel strength. And very much important is the elongation, A5, where we are conserving a elongation more than 8% in all the three thickness. And this is, it's thanks to the absence of segregations. We have no perlite promoters. And you are seeing that the results that Stefano got on the rotating bending fatigue, you see that the rotating bending fatigue is similar for the two materials because it is driven by harness. These are not the material that, the same material as Stefano presented, but they are data from our statistical database of our materials. And you see the comparison of the unnotched Sharpie impact energy at three different temperatures. Room temperature on the left, -20 at, no, it is just a moment. Room temperature, yes, this is all room temperature, but for three different wall thicknesses, 25, 50, and 75 on the right. The round points on the left, on the low strength, it's ferritic grades. Ferritic, that when you have silicon solution strengthening, as much as you go over 600 megapascal strength, the Sharpie is decreasing. The red dots are related to the conventional perlitic ferritic ductile iron in the mold, and you see that they are below 20 joules at 25 thickness, and they are a little bit decreasing when the thickness is increasing, and the upper black dots are really are referred to IDI, Isothermed Ductile Irons, the round with the low silicon, with the 2% silicon, while the triangles are referred to a silicon content of a 2.5. So increasing the silicon content, the Sharpie is decreasing a little bit. But you see that anyway we have a great difference between the conventional perlitic and the IDI, the isothermal ductile iron, with a superior strength. These are the same diagram at the -20. These are the same diagrams at the -40. So you see that with this material you can get much better properties, mainly in terms of ductility and toughness, that you can get with any other process of ferritic ductile irons. To have more, you need to go on Austemper ductile iron. But you know that with Austemper ductile iron, when you increase too much the thickness, you are obliged to introduce moly, and moly makes segregations that are in some way detrimental for properties. So this is that material, and the second part is the plastic flow assessment. So we need to have a process control tool that is able to ensure that we are able to maintain the properties of our material in the process, between the processes, and within a single batch. And this we are proposing to do alternatively to microscopic examination by the analysis of the plastic flow of the tensile test curve. And we are dreaming that in the next future to be able to build a machine, a tensile test machine, that after the test gives numbers, as you will see, that are representing the structure, the dislocation motion. That is, that give the properties of the material. This is based in cooperation with the Centro Nazionale delle Ricerche, that is the state research important organization in Italy, that where is coming this idea that we are implementing with them, that using the Voss equation, that this Voss equation is representing the material behavior, this dislocation motion, when you arrive to the considered condition. So the S in the A equal to 0 in the engineering curve. And this is very nice, this approach, because you see on the left diagram there is the representation of the experimental points of the derivative of the sigma in the epsilon plastic for the true curve, and you see that this analysis is measuring the line that is interpolating the final point, and so measuring the dislocation motion at the end when you approximate the maximum of the engineering curve. Getting two parameters, parameter theta 0, that is the amount of the epsilon axis, and the other one that is the slope of the curve, epsilon c. And and this has been tested with I used the same curves of the tensile test that Stefano was looking from the point of view of crack propagation, in 3 different wall thicknesses, 25, 50, and 75. So 75 is the thickest line, the 50 is the medium line, and the 25 is the thin line. In red, as usual, you see the conventional ferritic ductile iron as cast in the mold, while in black you see the IDI, the isothermed ductile iron. And you see here, this is the true plastic flow without the elastic component. And you see how the effect of no segregation, no alloy, no addition is very important as much as the thickness is increasing. So this is a demonstration that this material, IDI, is a very good material when you have no uniform thickness castings. You can have a different thickness and you can get approximately the same properties all around the casting. It is the only way we know now for the ferritic grades. And this is the microstructure quality assessment diagram that we learn to use in our company under suggestion of Centro Nazionale della Ricerca, where the 2 parameters theta 0 and epsilon z at -1 are represented, and you see that the different material has a significant different parameters, both parameters in this diagram. And to be in the right way in this diagram is a demonstration of the repetition of the process of our materials. In black, you see on the left, you see ferritic grades. In blue, you see the ADI materials that Stefano tested, and so the big dot is 75, medium is 50, small is 25, and you see that in ADI there is a difference for the 75 thick sample because of the addition of alloy elements we are obliged to capture this kind of thickness. And on the right, up right, you see the ferritic materials. The red one is a conventional as cast, and the black one is the IDI. So you see they are in the same range because the matrix is ferritic, but the difference is on the other side in impact values. Okay, and with this VOS approach, with this matrix assessment, we are able to assess the matrix independently of the presence of small defects. You know that one of the main concerns we found we have in our normal day life is that elongation at fracture is very dependent on the presence of very small defects. Because in the monoaxial, uniaxial tensile test, the small defects are dropping down in very significant elongation. This is not a question of material quality, but is a question of a soundness of the casting. And this is a very large field of discussion with designers that it is difficult to understand, to make us understand with them, and this is the reason why the international standards are so poor. What does it mean, ductile iron 603? It's something that does not exist. It seems as a brittle material, and it is not, we know. And so we need to measure the matrix properties independently from, and we found that as far as the amount of defect is in the normal range, not too much, it is possible to have this measure that is independent from the defect presence. So that one is a quality diagram of the matrix. But in any case, we need to measure also the presence of the influence of a micro defect. I mean metallurgical micro defects at the grain boundaries. And so this is measured with another diagram. Here you see with the considered condition. So it can happen that the test probe is breaking before the considered condition. And so we need to measure this. These are only formulas. This, you see in this diagram, you have translated in engineering numbers. A5 is what we measure in reality in our test, and epsilon, not epsilon, EUTH is the theoretical uniform elongation that we calculate with the Voss analysis. And you see the straight line is bisettrice in Italian, I don't know how it's in English, okay? That is where A5 is equal to E1 theoretical. And you see that ferritic ductile iron with the low or high silicon doesn't matter. In this case, it is with the normal silicon, and with a different thickness of 75, 50, and 25 are necking. They are necking. They arrive easily to the considered condition, and they go over the considered condition. While you see that the ferritic grade, the blue are ADI. ADI, they have a very good elongation. But the considered condition that we calculate with Voss, that could be different from what we see on the machine, because there are inertia on the machine, is a complicated thing. They are not able to reach the considered condition because the strength delivered is so high. So they are breaking before. And pearlitic grades, because of segregation of copper alloying elements we put to obtain the S-cast pearlitic, these grades are typically breaking before the considered condition, theoretical considered condition calculated by Voss, while the IDI, the isothermed ductile iron, is breaking approximately at the considered condition, as a demonstration of the importance not to have segregation at the boundary grains. This was also proposed for aluminum from Cassere and others since time to measure this quality index. For aluminum, in reality, it is a little bit more difficult than in iron because of the slag diffusion. We remember that in aluminum, the slag has approximately the same density as the liquid. So it's another thing. However, the idea was already taken in consideration, and for this reason, the proposal of a Centro Nazionale di Ricerca has been also to move with the iron on this field. Okay, so this is the assumption that we make that with iron the defect density is not so diffuse, is concentrated, that it enables us to use the fracture mechanics on one side and to use the separation principle from the matrix quality and the defect influence. That's all. Okay, this material obtained, I was surprised very easily, granted patent in Europe, United States, China, Japan, India, and Hong Kong. And we are open to discuss with end users and foundries the possibility to have a cooperation license for the diffusion of this material in the world. Remember that producing ADI you need very strong, robust furnaces, because you need to have a very strong quenching capacity, drasticity. Otherwise, stable austenite is not possible, and you have to add overalloy. While to produce this kind of material, the sole bath suitable for IDI production should be much more economic. And so the diffusion of this material could be much more intensive. Thank you very much for your attention.
Thank you. 2 minutes for discussion, please. Yes, please.
Including your results concerning failure conditions. A general consideration of Hans Zeuner, about 50 years ago, may be interesting. He said, if the cast iron world will be successful in competition to aluminum castings, the cast iron alloys must have the three times the tensile strength, because the relation between the specific weights is about 3 to 1. And he started with 500 for aluminum and forced 1,500 for castings. Steel castings were reached and successful, but they had to be alloyed and a specific heat treatment. And if you see the development ADI now, we reach these regions 1,000 and more Newton per square millimeters for castings by this new development. And I think all who have contributed to this development must have our thanks, and I wish very good further success in this development. It is a wonderful development of castings in the world of lightweight, because lightweight is one of the most important possibilities of the future. Thank you very much. You have contributed, and a lot of others in different countries were successful, and we will be very grateful and hope this can go on successfully. Thank you very much.
Thank you to you. Thank you.
Other suggestions, discussions, questions? If not, thank you once again, Mr. Zanardi.